recording, and then I will start presenting now. Then let's do this. Okay, so we are looking at Lambda calculus, and the last thing that we looked at was so something about church numerals, right? And what we said was we will actually show that the church numerals, the encoding of church numerals in Lambda calculus actually correspond to our intuitive understanding of what natural numbers mean in Coq. In particular, we'll prove something about things like the +1, and we will also prove that the add function that we described using Lambda calculus encoding behaves similar to how an add function should behave if we use natural numbers. Right? So that's what we are going to do. So let's have a look at the Coq definitions of these. So I'm going all the way back to okay. So I'm going all the way back here. So church numerals, right? So 0 as f of x is x, and +1 is takes a natural number and returns a natural number, where all it does is it takes f and x, applies to n, because any natural number takes 2 arguments, and the thing it does is it wraps another f, an additional f here, and that is precisely capturing the meaning of a +1. So there is an additional function that is wrapping around, right? So the first thing we'll do is we will actually define these 2 functions. So this function, right, which takes a natural number and relates it to church numerals, but without this outer wrapping of f and x, right? We call it canonical prime here. So 0 is x, 0 is x, and n+1 is f of this term, right? And n+1 is f of the term here. We recursively call canonical prime on this one. Again, the reason why this appears this way, you could actually do reductions here, and the reason why we don't do it is that our evaluation semantics is copy value. So it's not normal order, it doesn't reduce within the body of the lambda. That's the reason why this looks larger than it should. Right? So, and that's canonical prime. We want a definition of canonical representation, and all that is doing is wrapping a lambda f, lambda x around the canonical prime definition of the natural number. Right? So canonical is just a definition that wraps f and x around the canonical prime definition, a result of calling this on some natural number n. Okay, so that's canonical. So that's the canonical representation here. And we also have this relates definition. So this captures the relation between a church numeral and a natural number in Coq. If you can big step evaluate the church numeral all the way to the canonical representation of the natural number, then we say that these two are related. And essentially that's it, right? So we have the definition here precisely. So we say that this expression E represents the natural number n if you can evaluate E to the canonical representation of n. Right? That is all matters, and we can prove that it holds for a 0 and +1. As in the +1 really acts like the +1 in natural number. Right? Let's do 0 first. 0 is easy, right? 0 is sort of the base case. So we have multiple definitions here. So we have represents definition, right? Definition here. 0 is also a definition. And then we will have canonical, right? Because represents internally calls canonical. Canonical is also a definition. So we unfold all of these definitions, right? Once you do that, you just simplify. This is a fixed point. Canonical prime is a fixed point. So you simplify. We get the same term. So this is saying that if you evaluate a lambda, you get a lambda back, and this is directly appealing to the constructor, right? So which constructor you can do info e auto, right? Yeah, that's the big apps, right? Big apps is the rule. Like, let's not go back. We can even check it here. So big amps is a rule which relates a lambda. So it says that if you take a lambda and then big step evaluate it, you get the same lambda back. So it's just directly appealing to the truth. That goes through, right? And then next we want to say, I mean, these are getting more interesting now, right? So the encoding of our successor, this +1, is actually behaving like the natural number addition, right? So if E, for some expression E, if E represents the natural number n, then +1 of E represents n+1, right? This is quite nice. We sort of didn't do this, right? We just took the word for it in 3100. We can actually prove it here that it behaves just like a natural number should. So again, we do unfold of +1 represents and canonical. We simplify, right? We get this big term, right? And the thing to do here is to actually look at what we have. What does it mean, right? So evaluate relates the expression here to this and says that if you have this expression, you can big step evaluate down to this expression. So evaluation, the reductions have to happen within this expression, right? And this happens to be an application, right? So this is the whole expression, and this happens to be the left-hand side of the application at this application, and this is the right-hand side. And we know what has to happen for an application. Big-step evaluation semantics tells us that if you see an application, then the left-hand side must be unified with a lambda. If you big-step evaluate it, you will get a lambda abstraction. The right-hand side could be any value. You just evaluate some value, that's that value, and then you do the substitution, right? So what we are calling here is we are saying apply the Z constructor that will apply the rule for the evaluation, right? The application rule. I think this is big app rule. Let's go back and find it. Yeah, it's going to appeal to the big app rule, right? And that's the reason why you get 3 subgoals. Right? So because we appeal to this rule, so that we have to show all of the preconditions also hold. Okay, and then what do we have here? We have this term, right? And we are saying that this should unify with this. But the thing is, this whole thing is a lambda abstraction, right? So so n is going to unify with this unification variable x, and then e1 prime, right, is going to unify with this term. We are appealing to the big abs rule here. Right? So that gets substituted. So the substitution happens here, right? So wherever you see x here, this is unified. So if you simplify, yeah, that got replaced by n here. So we are just appealing to that. Now we are saying that you can evaluate E down to some value v2, right? And we have that as part of the assumption. Right? So we say if you evaluate E, you get this f of x canonical prime of n. So let's directly appeal to that. That goes through. Now we have to show some term here, but you see that there is a substitution. Substitution is a fixed point, right? So we can simplify it. So let's simplify the substitution. And what you end up having is the same term, right? Once you substitute, you just get the same term here. And this can appeal to the big abs rule, so that goes through. So what we've shown here is we've actually shown that the +1 that we define in this church encoding actually behaves like successive function in natural numbers. This is good. So let's extend this. Let's do additions as well. So additions here is takes two natural numbers, right? And then it applies n applications of +1 over m, right? So that is precisely what we have here, right? So that's addition, and addition works as you would expect, right? So this is an example that shows you can add 1 and 2 to get 3. So it says if you evaluate, adding +1 of 0 is 1, right? And then +1 of +1 of 0 is 2. So if you add 1 and 2 and you big step evaluate it, so you get some v, right? And the way we describe it is interesting. We say that the result form that you have, right, is the same as evaluating um, +1 of +1 of +1 of 0 to v. The reason why we don't directly write this term right here is that we have what do you say? So these two terms are beta equivalent, right? Both of them reduce to the same value, but they are not going to be alpha equivalent, which means they are not going to be syntactically the same except changes to these bound variable names. Right? That's the reason why we have to write it in this way. So we say that um, if you evaluate this function down to v, then you evaluate this function down to v, then they will have the same form, right? Then they are going to be actually the same term. This is not even alpha equivalent. This is going to be saying they are exactly the same term, right? So that's a quirk that we have to live with here, right? So um, really, if you wanted to sort of even if you had, say, just thinking through, right? Even if you had full beta reduction, you can't write this term directly here because this term could be further evaluated, right? And that's the point. Really, this is the only way to write this nicely. To say that this intuitive definition that applies these functions is going to evaluate to some value that might be looking very complicated, but what we claim is that both of these evaluate to the same value, right? So that's the reason why we write it this way. Okay, so let's do Ex is propositional to break it down, right? And all we are going to do here is, in order to evaluate it, we are going to repeatedly appeal to the constructor, right? That is precisely what we are doing here. And then try to simplify it. Of course, simplify is not going to hard fail, right? If it cannot simplify. So we repeatedly call E constructor simplify until we know that this is going to evaluate, right? Until the whole thing is reduced to some lambda, at which point this will just return. The goal will be done. So if you repeatedly apply E constructor simplify, it reduces, and it reduces to a huge value, but that's fine, right? This V reduces to a big value here, and that's the scary value that scary looking value that appears here, right? It's just expanded in place all of the definitions, but that's fine. Now, all we have to do is to show that repeated applications of this one is going to be exactly this term, which it will do. You can take my word for it, or you can apply E constructor step by step, and you can see that this is in fact the case. So yeah, so if you repeatedly apply E constructor, that will eventually reduce to the same value. I encourage you to step through it just to see how that form eventually goes through. It goes through because it will eventually reduce to something that is exactly the same, right? So it's not even going to be different. We are claiming that they are the same terms, so it's going to end up looking the same. But yeah, but that's the idea there. Yeah, okay. So we proved, I mean, this is what we ended up doing in 3100, right? We said, oh, you can have these simple examples where you add 3 plus 4, and then see there is 7 Fs there. We don't have a nice form here because we are using call by value, but we can go beyond, right? We can actually say addition behaves like addition of natural numbers as built-in cock. So let's do that. So in order to do that, we are going to use a few lemmas, two lemmas here. The first one is very simple. So if you look at the definition of canonical prime of n, right? Yeah, so if you look at the term that is produced for canonical prime of n, the only variables that we have here are f and x, right? N is a natural number, but all you end up building is a term that has f's and x's, right? So what this theorem sort of captures, I mean, this lemma captures, this lemma will be handy when we actually prove addition. What this lemma captures is that because canonical prime is only going to end up having the variables f's and x's, right? If you substitute some term m, right, for the variable m in this term, which does not have m, right, the substitution will have no effect because the variable is not there, right? So the substitution will not have any effect. So you will be left with the original term, right? So this is what this is capturing. This is intuitively true because there are no m variables within canonical prime of n. We will use it later, and this is sort of uh, it might be surprising why we are doing this here because we've done it backwards, right? So we sort of did the proof and then we came up with the lemma that we needed to prove. We proved it. Anyway, so I'm presenting it in reverse, but the proof itself is simple. You can induct on it. Again, I'm not going to walk through the proof because it's so simple. Okay, so let's skip the lemma and then come to the main theorem, right? So this theorem is what we have here. So if expression n is related to n and expression m is related to the natural number m, then if you apply this add function on church numerals on these two expressions, then that term is related to n plus m. Right? So if ne represents n and me represents m, then adding ne and me is equal to n plus m. So we are actually proving that the definition of addition that we have is correct with respect to addition as defined in Coq, right? So we have represents, which is a definition. So unfold, represents, and simplify moves a bunch of things to the hypothesis as well. And then there is a bunch of applications of constructor, right? So if you look at this term, this is a term that has application, and we know that add is also some function, right? So we can reduce it. Actually, it has two applications, and the application is left associated, right? So you first apply here, and then to the result of that, apply this one. So you call e constructor. It's going to give you three sub goals because of this big app rule that we are appealing to. And in turn, this one is also an application, right? So we do that, we will have that goes away, but we have three more. So we end up with 5, right? And now we have add, and we want to show that add evaluates to a lambda x0. And this is easy, right? Add is represented as a lambda, so that one goes through. And then we have to show that ne evaluates to some value, and we have that hypothesis here. So we call the assumption that will go through. We have a substitution here. Let's simplify the substitution. Right? And now again, we have a lambda here, right? So this is lambda m something in the body, and then this is lambda x with a unification variable e1 prime. This cannot be reduced further. So a constructor will just make it go through, right? So what will happen is that where you find say x is here, this should be substituted with m. So let's see whether what happens. Yeah, that happened, right? So that got unified and it was substituted away. And you have eval of me goes to some v2 that is also part of the hypothesis. So e assumption makes it go through. Again, substitution is there. Let's simplify. So keep doing this, right? So there is you've done one substitution. So if you look at this term, right, there is an application, right? So this is the left-hand side, and there is an application of something, and then one more thing is available here. So you have to keep doing the same thing that we did. So appeal to e constructor, e constructor, e constructor. You keep repeating that. If you end up with a substitution, we do the substitution. So we simplify uh, e, e constructor again, right? Then e constructor, it's go through. Finally, what you end up having is this term, right? There is something complicated here, but we defined this lemma earlier, right? Which said n canonical prime of n, which does not have this variable m, if I substitute some term, right, some term canonical m, for it doesn't matter what this term is, for the variable m, it will leave this canonical prime of n unchanged, right? That's the lemma that we prove. So we are appealing to that lemma. So what will happen is that this whole term will be replaced by just canonical prime of n, right? So that has happened. And now what we end up doing is we prove the rest of it by induction. We've done all of the substitutions and everything. So we prove the rest of the proof by induction on n, right? So because it's going to appeal to canonical prime of n, and we induct on n and prove it. And the proof is in this separate lemma, this R prime OK. And the, the way this is sort of organized is that I'm doing all the interesting stuff for the main theorem here, right? And I sort of offload whatever the state of this is into a separate lemma that is just a copy paste of this, right? And I'm proving this by induction. So if you induct on n, you will have to prove for 1 for 0 and 1 for n plus 1. Yeah, 0 goes through. Actually, I won't go through all of this in detail. So I want you to sort of step through it and see what is the rule that is applied, right? The only thing, because lambda calculus is so simple, right? You can only do a few things. You can do, you can only apply two forms of, you can only apply one form of reduction in big step semantics. The only rule is you have an application, you reduce the application. That's it, right? So, and that is what these constructors are doing. And if you end up with a value, big step evaluating that value, this lambda abstraction is just going to give you a lambda abstraction. Is part of what happens. Otherwise, everything is very simple. So I won't go through this in detail. By now, you should have the skills to go through it, right? So that goes through by induction. There is no complexity there. So what we've ended up proving is that the add function actually behaves like addition of natural numbers as defined in Coq. The original Coq sources also have multiplication that follows a very similar strategy. So have a look at multiplication in your own time. But let's move on to something more interesting, right? So, so we saw two ways of doing. Okay, let me move here. So we saw two ways of doing semantics in the operational semantics lecture. So we said you can do small step semantics or big step semantics. So we did big step semantics previously. Now we are going to do small step semantics, right? In fact, in 3100, I had introduced small step semantics. I didn't introduce big step semantics. There was a reason to do that because I really wanted to show where the evaluation happens when. And typically, people don't. This just I may be biased because I work on things like concurrency and parallelism and distribution, where big step semantics are not useful, as we've seen, right? You cannot express the non-determinism. But typically, right, you will see that papers tend to use research papers, and people who work on programming languages tend to use small step semantics more. It's just found favor a lot. Big step semantics is useful, but because it only says something about the end execution, having a bias on the papers that I'm reading, I see small step semantics more. Anyway, so here is small step semantics. Unlike 3100, I'm using evaluation context for describing the small step semantics. This is again call by value, right? So there is an interesting observation here. So this is the evaluation context, right? The evaluation context says that a whole is an evaluation context, right? And if you have an application, then you can have the evaluation context on the left-hand side of the application, the function position, and um, you can also have it on the right-hand side, right? But there is an implicit well-formedness condition, right? In order to have the whole, right, on the right-hand side term, it better be the case that you already evaluated the left-hand side to a value, right? So this is a very neat way of ordering these rules, right? Um, Unlike, say, I mean, what's the good way to describe it? So unlike, say, the parallel construct, where we said, oh, you have, say, E1 um, um, composed with parallel composition with E2, you can reduce either one, right? Here, this is not giving you non-determinism, right? I can't choose to reduce the argument position before I have actually gone ahead and reduced the function position to a value, right? What is this saying is that it is actually establishing a order of evaluation for the arguments, right? So if you, I mean, this is called by value essentially. So it says that you first reduce the function position to a value, then you go ahead and reduce the argument position, right, to a value. And this is giving, I mean, this is actually quite nice, right? It is actually giving the order of evaluation of the arguments. Uh, I mean, terms in an application. Let's not call it arguments. So even though there's only like a one letter change, right? If I put it as E, there is non-determinism, right? I can either reduce the argument first or um, uh, function first. But if I make it as V, I'm sort of forcing the evaluation of the function position first, because the only I can only go ahead and look at the argument position when the function position is down to V. I mean, these are like I mean, these are very nice properties, right? So you can describe multiple semantics by just changing a single letter. And that's I mean, this is one of the nice, and this is why writing semantics is useful and beautiful, right? Because with just a single letter change, you get a completely different semantics for the programming language that you're studying, right? So it's quite nice that way, but it's quite subtle. I think I thought I should bring that up because it's actually enforcing a call by value. Right? So okay, so that's evaluation context, and and we actually have to give a step rule, right? How do you make a step? The thing that we have now is because we have evaluation context, so this C would have evaluated down to a V. This C would have also evaluated down to a V, and the only thing that is left is the actual application, right? So the application expects left hand side to be a lambda, right hand side to be a value, right? This is again a V because this rule can only be applied when the right hand side is evaluated down to a value, right? This means that this is not call by name, right? Because this only applies to a value. If it were more complicated expression, you cannot do the substitution, right? That's actually forcing your hand. But otherwise, the substitution is straightforward, right? So you just do V for X in that whole. So this context as a whole, and the command happens to be a substitution. You just do the substitution and replace it back. And of course, you can once you define the small step semantics, you can go ahead and show that the two semantics are related, right? So if you sort of evaluate small step semantics down to a value, then the big step semantics also evaluates down to a value. If the big step semantics evaluates to a value, then the small step semantics values to a value as well. So this is important distinction, right? We say it's a value here because even the untyped lambda calculus is Turing complete, right? So if you evaluate, if E happens to be omega, then this omega arrow star does not evaluate down to a value because it will always evaluate to omega, and omega term, which is an application, is not a value. The only values in lambda calculus are the abstractions, the lambda terms, right? So it's hiding that subtlety. It's only talking about terminating programs here, right? So when we say a value, we say that implicitly the term is not a complex expression. It's actually reduced to a value. But that's that, right? You can prove that these two are equivalent. Yeah, okay. So let's look at the instantiation of this in Coq. Okay, so what do we have here? We have a whole. We have evaluation context appearing here with arbitrary expressions, but a value and the evaluation context, right? So, so we sort of actually do that in two steps. Here we say a whole, right? Evaluation context, and context can appear here with arbitrary expression, but we also have app2 which says expression context context, right? This definition is slightly different from here because we don't enforce that the expression itself is a value. Where we do that is in plug, right? We also have to define this plug relation that relates how do you take a evaluation context, plug it with an expression, and you get an expression back, right? Take an evaluation context, plug that hole with an expression, and it relates that to the final expression that you would obtain. So plug hole is straightforward. If you plug a hole with E, you just get an E, right? Plug app one says that if the context is app one with the whole, we don't use a capital C here, we are using a small c. But anyway, so the context is C here, right? And E2, and you plug the hole in the context with E1, right? And I say that the resultant expression is going to be app E1 E2. And all I'm saying as a precondition is that if you happen to plug C with E1, C with E1, you get an E, right? You get an E. So that's what the plug app one is saying, and that corresponds to plugging something that looks like this one, right? But here we are going to enforce this well-formedness constraint that this V has to be a value, right? So this is the subtle point that is also described here. But anyway, so if it happens to be an app2 where E1 is some expression, actually E1 has to be the value here, right? So that is what we capture here. So we say that you can plug the evaluation context app2 with E1 and C only if you can show that E1 is a value. So this is what is actually forcing this to be a value here, right? And you are filling the hole with E2, and if you fill the hole in C with E2, you get an expression, then you get an expression out. I mean, if you drop this, then it looks very similar to app1. This expectation that E1 has to be a value is sort of forcing call by value semantics. Okay, so that's the subtlety there. And yeah, so those are contexts and plugging holes. We have to define the step function. We don't actually do it in two steps here. Recall that when we introduced contextual small step semantics, we said we have a step 0 and a step C because we only have one rule, right? So we just directly define a step here, right? And the idea is that you can step from E1 to E2, right? You can step from E1 to E2. And what is E1? E1 can be separated into some context and application, right? E1 can be separated into some context and an application, right? And similarly, E2 can be separated into some context with a substitution in the body, right? E2 can be separated into some context with a substitution, right? And V happens to be a value. So this V is a value. So so yeah, so that that forces call by value semantics, right? Um, the only interesting point here is that we don't do it in 2 steps. Okay. So let's actually go and prove, say, this. Um, yeah, let's see. So let's try to prove small step semantics is related to big step semantics first. So I am adding these constructors plug and step, right? So that E auto is going to automatically find the proofs for me. So let me add that first. The first thing that I do is similar to what we had done in the operational semantics lecture, right? You want to first relate a single step, and then you want to go towards multiple steps. So firstly, we define a lemma, step eval double prime, that says that, so the way to read this is you start at E1, right? E1 happens to be an application, right, of some abstraction lambda xc to v, and you can step to that, right? The step relation here says exactly that. You can step to that to an E2, where E2 happens to be a substitution, right? So you step from E1 to E2, and then if you big step evaluate E2 to a V0, then you can go from all the way from E1 down to the same V0, right? So because we don't have the step 0 step C step split, but we still have the complexity there. This is sort of standing in for relating the step 0 function to the big step semantics that we had in the operational semantics lecture. So I'm just, so if you sort of stare at it, these 3 terms, right, are the same as what I have here. And all I'm saying is that after this step, right, instead of saying this is step rule, I'm saying that if you take E2 and then big step evaluate to some V0, then E1 also evaluates to V0. This E1, which is the same as E1 here, always evaluates to V0. So we are actually proving this by induction on the various forms that the plug is going to take, right? So the various forms the plug is going to take are these 3 forms, right? Plug hole, plug app1, and plug app2. So let's induct there. So you'll have 3 rules there. I'm going to, so this is going to be, actually I can simplify and then I can invert the hypothesis. If you plug a hole with this term, we know that D1 is going to be the same term, right? I'm just going to sort of invert it directly here. So again, recall that if you have P implies Q implies R, invert of 2 is sort of saying invert this term, right? Invert Q. So I'm inverting 2 here. So that gives me the fact that E1 is going to be that term. This E1 is going to be replaced now. So if you sort of stare at that E1 got replaced now, right? So that's the information that I gain. And then I'm going to invert this as well. So if you plug a hole with some substitute V for X in E, E2 has to be the same thing, right? Because hole is sort of, if this these two have to be the same thing. So which is what we have as a rule. So if you invert it, you learn that fact, right? So wherever E2 appears in the rest of the goals, E2 is going to be replaced by subst VXE. So if you invert 1, right? Invert 1, that's the thing that you learn, right? So E2 got substituted away. I can simplify this. Now this is an application, right? This is an application. So you call E constructor. You just unify this with an E constructor again. This is so we know this is a value, right? V is a value, so we cannot evaluate V further. So let's invert H so that we get some assignments for that v is gone, but we are going to sort of that's the constraint that is captured here. The fact that we learned v is some lambda is represented as lambda x0 comma e, right? So that is obtained by inversion of this assumption, right? So we learned that, and then this is e constructor. If you cannot evaluate big step evaluate lambda any further, so that just unifies, right? And this is e assumption, so we get e assumption here. So I've gone through one step, right? But this sort of you can sort of automate everything by just writing semicolons, right? So e auto. Actually, there is no automation here. It's just a convenient way of writing things down. So I'm inverting C, I'm restarting the proof so that I'm back to square one. But I'm inverting C, inverting 2, 1, simplify. These things, right? E-constructor, inversion, E-constructor, E-assumption are all part of E-auto. So E-auto makes it go through. And then I have two other things. Those can be obtained by inverting H0. So if you invert H0, what you end up getting is that, oh, it has to be, so you're applying this one. So you applied this one and you got a V0. So it has to be the case that this is a lambda, right? And that is the fact that you learn, right? So E4 evaluates to lambda, right? E evaluates to some V2, and then you do the substitution. And the rest of it, auto makes it go through. You can do info E auto to see what, yeah, so there is a bunch of, there's a big app application. In order to say something about the application that appears here, right? So you can do E constructor. And then I'm appealing to the induction hypothesis, right? So I'm proving the rest of it with the induction hypothesis. All of those assumptions happen to be in the context, so those go through as well. Actually, let me not go through it in any detail, so you can do this yourself. This is not this is perhaps something you can do by yourself at this point. Has to have an index. No, screwed up this one a little bit. Okay, so this one goes through, right? So what we've actually shown is that single stepping, right, getting to E2 and then big stepping all the way to V0 would be the same as big stepping all the way from E1 to V0, right? So let's add this as a hint for E-auto. This is essentially step, right? So if you have these three rules, then if you have these three properties, then you can just that shows that step E1, E2 holds, right? So I've done like a explicit one here, but I'm just going to now appeal to step. So if you can step from E1 to E2, and then you can big step evaluate all the way from E2 to V, then you can big step evaluate all the way from V1 to E1 to V, right? So because I've added step eval double prime as part of the database, right? So E-auto actually applies that directly. So this is very simple actually. So yeah, so it applies directly to step eval double prime, right? Which is just what we proved. So you can take one step from E1 to E2, and then you can big step evaluate all the way to V. Then it means that you can big step evaluate all the way from E1 to V. So that's done. Now we have to relate, as we had done in the operational semantics, right? Multiple steps of E, if it gives you a value, right? And V is actually a value, that's another precondition. Then, I mean, this is sort of like saying that's the final state, right? Then then E evaluates to a value. And the only value that we have is the abstraction. Right? So again, um, you can let's go through this, right? So you can induct on this transfer reflexive closure, right? So you get two steps. The two steps correspond to the reflexivity and the TRC front, the transitivity, right? You can invert one. So X is a value. We know X is a lambda. So step evaluating lambda gives us a lambda, right? That's the idea there. So if you invert, you learn that this is a lambda, and then E constructor makes it go through. For this one, we first do intros just to push it up. And now we are going to appeal to the lemma that we prove here, right? So which is we have a single step from X to Y, right? And then we are going to see big step evaluation from Y to Z, right? So that's the reason why we are appealing to the lemma that we prove here, right? If you big step evaluate from y to Z, then you can go from X to Z. That's what we proved here. So I'm going to apply the lemma that I just proved, right? And now I'm asked to prove you can take a step from X to some state, and I know that state is Y, right? The assumption makes it go through. Yeah, and now I have to show that I can go all the way from Y to Z, right? And the Z is a value. And if you sort of stare at it, you have the assumption here, right? So you apply this induction hypothesis, you get one proof, you get one obligation, proof obligation, which is value of Z, which is made to go through with the hypothesis. Okay. And you could have automated all of this by just inducting on one and inducting on one here, right? The rest of it, we've already loaded enough of the constructors and these lemmas into the database so that eauto actually makes it go through. So that's proving that if small step semantics evaluates to a value, big step semantics also evaluates to value. I'm skipping the other direction. So if big step semantics, if you have big step semantics, it also evaluates to small step semantics. This is quite straightforward, right? So so that sort of concludes our study of untyped lambda calculus, right? Next thing we will do is we will actually encode simply typed lambda calculus. We will add types to the language, and we will show that well-typed programs do not go wrong, right? This is like the standard property that we have. Not going wrong in simply typed lambda calculus is that you are if you have a program that has a type that has no type errors, then it means that the expression, the term that has the type, right, can be either evaluated down to a value. I mean, it is always possible that it is evaluated down to a value. Not getting stuck is it is not a value, but you can't reduce it further, right? So we've seen a lot of this in 3100. I mean, we are going to do that much more formally here, right? We just reported those theorems there. We are actually going to show that these sort of bugs are the bug, which is that getting stuck is not going to be possible. Even this sort of underlies again. This sort of underlies the principle behind how OCaml operates, right? And OCaml says your program is type safe. It guarantees memory safety, right? So it says that you will never segfault. Similarly, Rust, right? And Rust says that your program is type safe. It guarantees something about the memory usage. Right? It says you don't leak memory. There are no memory errors, even without a garbage collector. Type system is more complicated there, but the type system guarantees that even without a garbage collector, you have precise memory management. Right? So I think those are like really great results, right? Rust is sort of a result of academic work that has happened over the past 30 years, perhaps, right? And the sort of principles that underlie the guarantees that Rust provides is very similar to what we will study in this, right? Rust does not have a formal proof. I mean, there is work to formalize the guarantees of Rust. But here is what we will see in the next class, which is the week after the next week, is we will study what that means, right? We will actually study very formally what that means. And it turns out that we can express this not using some new formalism, but using all the things that we've learned previously: operational semantics, transition systems, induction, invariant weakening, all of these little things, right? And it'll be sort of appealing to all those ideas that you've already learned. So we'll catch up with that next week. Okay, so I'll stop here, and all the best with any of the problems that you might still have left in the midterm, and have a good break, and I'll catch up week after next. Thank you.